For example 5, it says if y is equal to u cubed plus u squared plus 1, where u is equal to 2x squared minus 1, determine the derivative when x is equal to 2. So we know that we have the outer, we know that we have the inner. And we know that dy over dx is equal to the derivative of the outer, which is going to be 3u squared plus 2u, times the derivative of the inner. The derivative of 2x squared minus 1 is just 4x. We know what u is equal to, so we're going to state that that is going to equal 3 times 2x squared minus 1 squared plus 2 times 2x squared minus 1. And all of that is getting multiplied by 4x. And we're solving for when x is equal to 2. Which means we have 3 times 2 squared minus 1 squared plus 2 times 2 squared minus 1 all times 4 times 2. Or 3 times 49 plus 2 times 7 times 8, which is going to give 1,288. The second way that we could approach this is because we know that x is equal to 2, then we know that if u is equal to 2x squared minus 1, then u is equal to 2 times 2 squared minus 1, which is just equal to 7. So once we do the first step, where we said that dy over dx is equal to 3 times u squared plus 2 times u times 4 times x, then this is occurring where x is equal to 2 and u is equal to 7, which we just solved, which means that we can just sub that in. We can say that that is going to equal 3 times 7 squared plus 2 times 7 is being multiplied by 4 times 2, and that also gives me 1,288. So both methods are perfectly viable. A special case of the chain rule occurs when the outer function is just a straight power function. Suppose that if you get y is equal to f of u, which is equal to u to the power of n, where u is equal to g of x. If we use the power rule followed by the chain rule, then if we're taking u of n, we know based on the power rule that that is going to give n multiplied by u to the power of n minus 1. And that is still going to be multiplied by the derivative of the inner, the du over dx. Remembering that this first part is literally just the derivative of the outer. So, d over dx of u to the n is equal to n u to the n minus 1 times du over dx, or we can say d over dx of g of x to the power of n is equal to n times g of x to the power of n minus 1, all multiplied by the derivative of g of x. And just like before, this winds up just being the derivative of the outer and the derivative of the inner. So if I'm using that for example 6 here, where it says differentiate v is equal to bracket x cubed minus 1 to the power of 100, then all I'm going to state is that dv over dx is going to equal, just look at this outer shell. If I had something, ignoring what this is for a second, something to the power of 100, then I would just say it is 100 times that something to the power of 99. And in this case, I know that that something is x cubed minus 1. So what's in the brackets stays the same. Then I just multiply that by the derivative of what is actually inside the bracket, which is just going to be 3x squared. So in this case, the outer is just using the power rule for the brackets. The inner is actually just taking the derivative of what is inside of those brackets. And then we're just going to simplify. I'm going to have 300x squared times x cubed minus 1 to the power of 99. And that's my answer. Example 7 is very similar to example 6. If I need to know f prime of x, if f of x is equal to 1 over the cube root of x squared plus x plus 1, then the first thing I'm going to do is I'm going to rewrite what f of x is and state that f of x is equal to x squared plus x plus 1 to the power of negative 1/3. Negative to move it out of the numerator, and remember that we're going to take the index of the radical and make that the denominator of my power. Now I have the outer and the inner. The outer is just using the power rule with this negative 1/3, which means that for the outer part, for f prime of x, I'm just going to use that negative 1/3, and I'm going to say that I have negative 1/3. What's inside the brackets doesn't change because it's still the base, so x squared plus x plus 1. And then when I take that n minus 1, if I have negative 1/3 minus 1, then that's going to be the same as negative 4/3. Then I'm going to take the derivative just of what's inside that shell, or the x squared plus x plus 1, and the derivative of that is going to be dx plus 1. Once again, just like in the previous cases, I have the outer derivative and I have the inner derivative. This is going to give me negative 1/3 times 2x plus 1 times x squared plus x plus 1 to the power of negative 4/3. The 2x plus 1 is going to stay in the numerator. The denominator already has a 3, and now it's going to get that x squared plus x plus 1 to the 4/3, or negative bracket 2x plus 1 over 3 and the cube root of x squared plus x plus 1 to the power of 4. And that's it.